Hi everyone, so today we will look at problem 13 from the same exam that I previously picked question 17 and 18 from, which is the AMC 12A 2018. Problem 13, I wouldn't say it's a very difficult question. It's just asking about all of these combinations of numbers and then picking out the non-negative integers from them. So let's begin. So question asks, how many non-negative integers can be written in the form this, where ai is within the set of -1, 0, and 1 for 0 smaller than or equal to I smaller than or equal to 7. So at first glance, right, we are just figuring out all the combinations of A7, A6, A5, A4, all of these, the combination of those where A7 could be equal to -1, 0, and 1, A6 is also -1, 0, and 1, A5 is -1, 0, and 1. We're just trying to see how many pairs there are, which this one could be -1, -1, 0, 1, and then this could be -1, 0, and 1, and then this also -1, 0, and 1, -1, 0, and 1. So it seems like it's just 3 times 3 times 3 all the way. There are 3 to the power of 8, remember, because 7, right, to 0, including 0, that's 8, not 7. It seems like this question just asking for this number right here, 3 to the power of 8 combinations. But then we see they want the non-negative integers. So now we have to think about, out of all of these combinations, right, all of these, for example, -1 times 3 to the power of 7 plus -1 times 3 to the power of 6 plus 1 times 3 to the power of 5, like this could be one of the possibilities, right? But out of all of these possibilities, which of them make the whole sum negative? So apparently this one, if you set all of them as negative, right, it makes the whole sum negative because you're just adding a bunch of negative values together. So we're just trying to figure out which one of these combinations yield negative value, and then we're trying to eliminate these combinations. So first we need to figure out what makes the sum negative. What makes a7 to the power of a7 times 3 to the power of 7 plus a6 to the times 3 to the power of 6. What makes this whole thing negative? So you should observe that firstly, the starting value of ai decides the positive or negative value of the sum. What do I mean by that? So let's say A7, let's say that equals 1, positive 1. And then A6, A5, A4, all of them equals -1. So this whole thing would be 1 times 3 to the power of 7 plus -1 times 3 to the power of 6 plus -1 times 3 to the power of 5, and all of these. This would yield a positive value, despite the fact that only one of these is 1, but all the coefficients following is negative. So this one's positive, but the ones following are negative. How do we prove that? So actually, let me just define it a little bit clearer. The starting value, by that I mean not only a7, right? In this case, it's a7, but it could also be a7 equals 0, a6 equals 0, a5 equals 1. So the whole thing would be 0 times 3 to the power of 7 plus 0 times 3 to the power of 6 plus 1 times 3 to the power of 5 plus all of these. You can make that all negative times 3 to the power of 4 plus a -1 times 3 to the power of 3, blah, blah, blah. As long as the starting value, because these ones don't even count, as long as the starting value of this is positive, no matter how negative the parts after that, well, of course, the limit is just -1. You can't go -2, -3, because it's not asked in the question. So as long as you have this as positive, no matter how negative you go, the whole thing would yield a positive value. Same thing when it's negative. As long as this is negative, -1 times 3 to the power of 5, plus, when you make all of this positive, right, 1 times 3 to the power of 4 plus 1 times 3 to the power of 3, as long as this is negative, the whole thing is negative, no matter how positive the ones on the back is. So let me just prove this. So what does it look like algebraically? AI, right? AI equals -1. Or let's use the positive example first. AI is 1. AI minus 1, AI minus 2, AI minus 3, all of these are -1. So it's like 1 times 3 to the power of 7, or 3 to the power of I, because we're using algebraic value now. 1 times 3 to the power of I, compare that, or we're saying that it's bigger than the sum of -1 times 3 to the power of I minus 1 plus -1 times 3 to the power of I minus 2 plus -1 times, well, all the way, plus -1 times 2 to the power of 0, which is, well, this is 1, but we're trying to prove that this is true. So right off the bat, you should notice this is a geometric series. So I'm just going to rewrite the inequality. This is a geometric series. So how do you get the sum of them? So firstly, let's simplify it. So it's just negative 3 to the power of 0 plus 3 to the power of 1. Sorry, 1 plus 3 to the power of I minus 1. Which the sum of geometric series is basically, there's a formula. I can't remember, but I can just try to come up with that. So you have this. So let's say s equals negative 3 to the power of 0 plus 3 to the power of I minus 1. And then 3s equals negative 3 to the power of 1 plus 3 to the power of I. And then 3s minus s equals, all of these parts cancel out, as well as this one, because it'll cancel out here, this one as well. So 3 to the power of I minus 3 to the power of 0, which is, of course, negative. And then 3s minus s divided by 2, because that would yield 2s, equals s equals negative 3 to the power of I minus 3 to the power of 0 divided by 2, which is negative 3 to the power of I divided by 2 minus, plus 1/2. So right here we can rearrange the equation. So we're just trying to prove that 3 to the power of I is bigger than 3 to the power of I divided by 2 minus 1/2. See how the operators changed? The negative became positive, the plus became negative. It's just that we're trying to represent two different values. So this is 0, right? This is positive value. We're trying to represent just the absolute value between these two, which is the distance. Because as long as this is 3 to the power of I, as long as this distance, right, which has no vector, is just the magnitude, as long as this is bigger than 3 to the power of I minus divided by 2 minus 1/2, which is the distance, because that's the absolute value of this. As long as this is bigger than the absolute value of this, we can say that, oh, when you fold it over, right, you still have the remaining part. So you have this much remaining. You'll end up with a value here. That's just the way you look at it graphically. Look at numbers graphically, always. So this is what we're trying to prove. So firstly, this and this is the same. This is definitely smaller than this because, well, of course, there's no way it's not. It's just divided by 2, right? Any positive integer divided by 2 is, of course, smaller than the original positive integer. So that minus half, right, is even smaller than this. So basically now we have proved this inequality, because this is this divided by 2, smaller than this divided by 2, and then minus 1/2, of course, smaller than this. So now we proved that the starting value of positive, negative, whether it be 1 or -1, it will trump all of the values that come after that. So when this is 1, when this is -1, the whole thing, no matter how negative you get with the -1 times 3 to the power of I, the whole thing, no matter how negative it is, this would be positive. And then no matter how positive this is, this would be negative. So the second step is just trying to figure out what combinations there are after we acknowledge this fact. So how do we actually arrange it into real terms? Let's say we start with a7 equals 1. So that would mean that all of the values of a6, a5, a4 could be within the set of -1, 0, and 1, and then the whole expression, which is a7 times 3 to the power of 7 plus a6 times 3 to the power of 6, the whole thing would still be positive just because that a7 is 1. So 1, and then there are three choices for a6, right? -1, 0, and 1. Three choices for a5, three choices for a4, which means from 6 to a0, right, there are 7 different pairs of 3s, which means it's 3 times 3 times, it's 3 to the power of 7. 7 3s timed together because each of them has 3 possibilities, and yeah, you have 7 different pairs. 7 different pairs of 3s, right? Now we look at when a7 is 0, a6 equals 1. So ultimately we're just trying to find out all the positive and 0 values of this sum by saying that, firstly we have a7 is the starting value, then we have a6 as the starting value, then a5 is the starting value, a4. So all of these sum together, all of these combinations sum together would be the ultimate amount of combinations that would make this whole sum positive, and 0, of course. So a7 is 0, right? a6 is 1. The next step would be a6, a7 are both 0, a5 equals 1. So starting value would shift from a7, a6, a5, and then a4, a3, a2. I can't believe I heard before. Firstly, if you have a7 is 1, all of these combinations make a 3 to the power of 7. And then if you have a7 is 0, a6 is 1, from a5 all the way to a0, there are 6 different pairs of 3s. So 3 is like 3 possibilities, 3 different choices. So 3 times 3 times that would be 3 to the power of 6. And then this one, a5 is 0. A5 is 1. a4 equals 0, or, well, it could be anything, sorry. -1, 0, and 1. a3 is also this. a2, this. a1 is also this. a0, -1, 0, and 1. So from a4 to a0, there are 5 different pairs of 3s. 3 choices. So 3 to the power of 5, right? 3, 3, 3, 3. Each of them could pair a different choice. So 3 to the power of 5, and then a7 equals 0, a6 equals 0, a5 equals 0, a4 equals 1, right? That's 3 to the power of 4. And then we could just keep going. a7 all the way to a1 is 0. And then a0 equals 1. That would be 3 to the power of 0, because there's only one possibility, because there's nothing after. So it's basically 3 to the power of 7 plus 3 to the power of 6 plus 3 to the power of 5 plus 3 to the power of 4 plus 3 to the power of 3, 2, 1, 0. This is the answer we're looking for. This is how many combinations there are to satisfy that the whole expression yields a positive/0 value. So let's just calculate this. This is also actually a geometric series, which means that 3 to the power of 7 minus 1 divided by 3 minus 1 equals, is 3 to the power of 7? 3 to the power of 8, my bad. That would equal 3281. That's the answer. So let's see the problem. So yeah, this is choosing D right here, 3281. Now let's look at problem 9. So for the AMC, it has 25 questions on a single paper. From question 1 to question 20, it's like fairly okay questions, not occupying you a lot of time. And then problem 21 to problem 25, you probably need to put some serious thinking into this and then try to solve it. Problem 9, though, I think it's very, very straightforward. It's pretty easy as long as you're staying within the of course, this one's about trigonometry. So it asks, which of the following describes the largest subset of values of y within the closed interval 0 to pi for which sine x plus y smaller than or equal to sine x plus sine y for every x between 0 and pi inclusive. So comparing these values, right? First thing and the second thing you're thinking of, probably the first thing is algebraically converting this to something that involves sine x, sine y, and then find out the difference between the two. Second thing you're probably thinking is somehow on the sine graph, figure out sine x and then sine y. Y is from here, that should start here. Sine x plus sine y, actually this is better, here, and then somehow figure out the value of this and the sine y value, right? How they add up together equals or smaller than or equal to this value, right? So we're gonna do it algebraically. The second one, it looks good, but in general, I just sense a very strong feeling that we're going to use one of the trigonometry formulas, which of course it's what they examine a lot during high school math competitions. It's sine a plus b equals sine a plus sine a cosine b plus sine b cosine a. In this case, we can just substitute that with x and y equals sine x cosine y plus sine y cosine x. So just comparing this with sine x plus sine y. Immediately we can see that sine x, of course, it matches. Sine y, this also matches. For the value on the left to be smaller than or equal to the value of the right, this one has to be smaller than or equal to 1, as well as this one smaller than or equal to 1. We're just trying to figure out the range of y, where cosine y is smaller than or equal to 1. Let's look at the cosine y graph. So cosine starts from 1. It lands to 0 at pi over 2, and it reaches negative 1 at what was it, pi? Yeah. And then it goes back to 0 at 3 pi over 2. Sorry, it goes back to 0. So again, it just circulates like that. Ooh, yes. Knowing that cosine y is represented by this graph, we're just trying to figure out a period on which the cosine y value is smaller than or equal to 1. And then we kind of figure out that since this is the line that we're trying to see, all of this whole graph is just smaller than or equal to 1. So any period, whether it be cosine 3531, for example, or let's say 0.5, right? Or anything that should be smaller than or equal to 1. So just figure out which subset is the biggest out of all of these choices, which is, of course, E. And that is as straightforward as it gets. Also, just want to touch on why the cosine graph looks like this. So, of course, this is basic knowledge, but you can basically see it from the unit circle. Oh my gosh. The unit circle, right? The cosine is basically just comparing the value of this with the value of this. So value of this divided by value of this. So when the hypotenuse, right, it shifts this way, the value of this divided by this will change. So at the beginning, it's the same because they're sticking together, and then as you move slowly towards this way, when you reach this point, which is pi over 2, the value of the going this way is just 0, and the value of this is still 1. And when you go this way, the value of this goes negatively. Imagine this as a axis of numbers. So this is going negatively, right? But this is still 1. So negative, when you reach here, that's -1, and then the value of the hypotenuse is still 1. So yeah, that's it.